Come on. People are appearing and disappearing. Appearing and disappearing. Two more minutes. I'll start in 2 minutes. This is fine. So, time to start. Oh. Oh, hello. Hello, hello, hello. Anyone? Oh, I think I can start. I think I can start. Yeah. I think I can. Ah. Oh, time to start. Time to do something. I have a nice program. This program is doing very simple thing. It draws a chart of rectangular signal similar to one we saw previous lecture. I can also repeat what we done before. Something familiar, base frequency or base harmonic of my signal. Third harmonic. The orange line is what we saw previous lecture, yeah? I can put as many harmonics as I want. For example, 10, okay. Here is the first 10 harmonics. It's more precise, yeah? Okay. First 25. Well better. First 100. Better, isn't it? But this, you see this tiny problem? This spike do not disappear. First 250. Spike do not disappear. Can you see the spike? This one. And this one. And this one. Maybe I'll take less to make it more visible. This. All time when original signal light goes through a breakpoint, we see this oscillation. It's a, how to say, piccat originalum of Fourier law. It's a nature of Fourier law. When signal has a break, Fourier law do bit strange thing. It oscillates around the breakpoint. The let's say source of this problem, signal has a break. It's like a commutation in the point, in my case at 180 degrees. But Fourier law is uninterruptible. It's a conflict. For the many years, no one was able to, rectify this error. It was clear. It was clear at the first day. Lagrange, famous Lagrange, pointed this problem and refused to publish Fourier article. You make a mistake. Your idea with the law we are speaking about error of the Fourier law. So, famous Lagrange pointed this problem. No, this will not work. Dear Lagrange, everything not so bad. But when you substitute and interrupted something with the Fourier law, you will see this. It's because of nature of the how to say, the first basic foundation of Fourier decomposition. Because Fourier selected factors of his law to minimize an average error. Fourier law converges to original, but converges in average. Here is a result. When you have a sharp change, you see this oscillation. And how serious is problem? You can see, if I take, for example, 100, energy of this difference, you see, it goes to nil, to zero. Because the spike will become an infinity thing. So energy of difference between between Fourier, is the composition result, and original will go to zero. But amplitude, not. I don't know if I can put 500. You see spike remain. It will not disappear. Okay, let's say 15. Oh, nice oscillation. For the long year, there was no solution until famous physicist Gibb put his attention on this problem. And from this day, this behavior of Fourier law is named as a Gibbs paradox. Where is my Gibbs paradox? Can I switch to, I can do it like this. Okay, it's fine. It is fine. So, idea. I have, as I described Gibbs, let's say I have an x, and y being a function of x. And I have a breakpoint at, let's say, point A. In the if epsilon going to 0 of f of A minus epsilon is A capital, and limit epsilon goes to 0, A plus epsilon being B. I have an interrupter function. What will be mistake, what will be error of Fourier law? What will be the difference? It's like Gibbs put it. What's the idea? Let's try to separate the break. Let's introduce a function g of x big minus 1. Let's say x 0 and 1 from 0 g no x, Gibbs function. It's a Gibbs function. Amplitude 1. It's our familiar rectangular function with the e being unit. And draw here, draw it not as function of time, but as double period. Use this as argument and you will get our previous function. Introduction of Gibbs function. What it gives us? And so on and so on and so on. Double period. And so on and so on. Gibbs function. What can I write? I can substitute Gibbs function with the Fourier law. It will be 4p multiplied by sine x plus 1/3 sine 3x plus 1/5 sine 5x blah 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 equals to 4 divided by p sum. I change from 1 to, let's say, infinity. Sine of I minus 1 x divided by I minus 1. Sorry, double. Yeah, it's, I should be correct. I should write 2I minus 1 x. Yeah, now it's correct. Double I minus 1. Here is the Fourier law for Gibbs function. Easy. Original function can be now substituted by half. Gibbs function from A plus some, let's say f1 more x, some function with uninterrupted, without interruption. So, why Gibbs doing this. If it will be possible to estimate error or this, let's say, deflection from the original of this Gibbs function, it will yield what? Upper estimate for any error of any Fourier substitution. If it will be possible to calculate this level, it will be upper limit for error. This discrepancy. Oh. So problem here, original function has a limit a on b, independence from which point we are, from which side we are approaching, but Gibbs function has its limit 0 at the breakpoint. We have a, let's say, source of discrepancies here. But yeah, we see discrepancy, but can we estimate it? So, Gibbs idea. Let's try to investigate function as n from x being 4 divided by 3 sum at I from I to n of z sine double I minus 1 x divided minus 1. Sum of first n members of the row. This digit is an n. Okay, now we see S15. Sum of first 15 harmonics. How can we, let's say, investigate? We need to analyze its first derivative by solving this equation, yeah? How can we find extrema? We need an upper margin or let's say, saving for the error. This means what we need to find an extrema point. Solution is simple. Solve an equation with the first derivative. Yeah? Yeah, easy. So I will need to solve an equation something like 4 divided by 3 cosine x plus cosine 3x plus cosine 5x blah 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 equals to 0. Sum of cosines. Any idea how to solve kind of equation? Yeah, it's not. Here the dog is digging. You need to solve cosine x plus cosine 3x plus blah 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 cosine for n minus 1 x equals to 0. It isn't easy to solve. Any idea how to solve it? I would say go to hell. But Gibbs was famous scientist with a good knowledge of complex mass. inside a complex mass, there is one of the complex rows like this. A power half multiplied by 1 plus 1 plus a power bet plus a power your double bet plus a power triple bet and so on plus a power m minus 1 bet. Nice row, isn't it? The good in this row, what it can be substituted as a power half multiplied 1 a power m beta divided by 1 minus a power beta. Here m is an integer. So what can you will ask? What's good in this substitution? You see something usable in this? Appears someone smoked something bad. Take a real part of this. So I can write this as applying Euler formula as a cosine alpha plus m minus 1 bet divided by half plus sine alpha plus m minus 1 bet divided by half multiplied by sine m bet by half divided by sine of bet by half. It's easy to find just calculating with the Euler form elements of the exponential row. Key interest here is this. This is a real part. If we take a real part what we will get? Real part will be cosine of alpha plus m minus 1 bet divided by 2 and multiplied by sine of m bet by half, and here should be sine of bet by half. So, what does it mean? Cosinus alpha plus blah 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 can be substituted with this assume what bet is double x and alpha x itself. And your problem with cosine will be solved. So the sum of cosine can be rewritten as cosine nx multiplied by sine of nx and divided by sine of x equal sine of double nx divided by 2 sine of x. Yeah. Here is the solution. Good to know complex mass sometimes. First, I can substitute sum of element with z 0 to x sine double n divided by sine. I can, if I knew the derivative, I can understand sum is an integral. But the key moment, first extrema can be found sine double nx equals to 0. Here, extreme point will be copy divided by double n, where is 1, 2, 3, so on. X this one and this extreme is k1. The first one, the biggest one, corresponds to k1. So here is the max error. And what will be this error? One second. I can write this one as double 2 divided integer from 0 to p divided by double m sine of nt divided by t dt equals to I will set y as 2n and t. This allows me to write by p from 0 to p sine of y divided by sine of y divided by double n dy. This is n. When n leads to infinity, I have a longer row. Y divided n goes to 0. And sine of y divided by double n can be substituted by y divided by double n. Sine of small angles is approximately angle. This means what this can be written as 2 divided by p, and from 0 to p, sine of y divided by y, the y is when n goes to infinity. So 2 divided by p, and this value, it's an integral sinus. This one is known from table. It's an integral sinus of p. And well, what we will get? We will get 1.179 blah blah blah. Do we have an answer? Yes, we have an answer. In the worst case scenario, this difference will be 18%. Gibb's paradox. Gibbs found a concrete say. What? In worst case scenario, mistake in amplitude will not exceed 18%. You know what this? What it was? It's a stator of asynchronous motor. Here was winding, in middle was rotor. While I'm showing it, see, grows where winding was. If you apply technique based on Fourier transform, here, where my finger is, it's a sharp change from the surface to groove. Surface, this slide for winding. At this point, I saw it in person when calculating field. What kind of oscillation? It's impossible. Possible. Gibbs give you a hand. Gibbs paradox occurs when you try to decompose into Fourier law or apply Fourier-based mass to something like this. It's a sharp change here when it comes from surface to winding. You will get this oscillation. Nothing, in not so sharp form, but actually I saw a so nice. The cutting from the winding was absolutely straight. It was a simple design. Brilliant. And an attempt was made to calculate field distortions. Calculated. Yes. Very nice charts. Very nice, but with little problem. But it's easy. Just cut like this, and it will disappear. Gibbs paradox occurs only on sharp changes. If you have, let's say, chamfering on your surface, it will not appear. I'm showing the worst case scenario. Okay. Some questions maybe about this? One? No one. Okay. Just remember it. What Fourier law on a sharp change oscillates, and deviation from your signal in the worst case scenario will be 18%. Now, what I'm going to show, first show example of discrete time Fourier transform. I would like, first I will switch to, we'll switch here. I have time, so I would like to show first application of discrete time Fourier transform. Repeating, let's say you have a periodic signal. Here m is an integer and t capital is a repetition time. You have the signal. I can. Here is signal. Let's say you have a table of values 1, 2, 3, 4. The last one in period will be n capital. Table of values. So you have signal values where I change from 1 to n capital. That's what you have. You would like to get a Fourier transform for this. Get ideal components of this. How can we do it? Original theory tells us what we can substitute our signal with 0 the DC component plus some from 1 to let's say infinity of cosine k double p divided by time plus sine factor or scale sine of k double p divided by time multiplied by time. It's a classic of Fourier law where say double divided from 0 to time my signal multiplied by cosines and S is double divided by P. I should integrate in the from 0 to time sine double P time against n in time. It's a classics of Fourier transform. But this for one day I'll be fine for each but not tomorrow and not today. I would like to do what? I don't like to do everything by hand. I would like to make machine do my job. Machine calculates. I relax. How can I do? How can I make machine to do my job? I can calculate this numerically. I can do it like this. And I have a table of values. Sum from 1 and value of this cosine of I minus 1 double P divided by number of dots and SK sum I1 sine of I minus 1 double P divided by N. I did a simple thing. I substitute integral of sigma by cosine blah 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 with a sum of rectangles. I'm assuming what area of this figure, white figure, can be substituted with a sum of this, let's say, rectangles or pillars areas. Easy. Now, how it can be in reality? 1 second, I'll switch to yeah. I would like to show this case example of the DFT application. Actually, it's our first homework. I have a table of signal. Here it is. I use CLab. You can use MATLAB or anything. It's not problem. Any mass environment will go. What's good in CLab, you can freely download it as CLab or org, free of charge. And it has sufficient mass inside to solve all our tasks. Simple syntax. I don't know what kind of programming language you have. Yeah. Okay, you will have CLab if not. It's a very simple language, very close to mass, natural mass. I will go, this means what I should go row by row. The first one is just a remark. 2 slashes mean it's for human, not for machine. Do nothing. Clear means to purge all variables. As MATLAB and other, let's say, this desk mass environments, classic executable clears all memory when started. This kind of environments keep variables until they are told to purge them. So this means purge all environments. This one simple defines a matrix of value. It will be a row. If I put a semicolons or write them as a colon, it will be column vector. Here it's simple row of values separated by spaces. You may separate by commas, but remember what as a native for programming language, point is a decimal separator. Here, let me go here, for example, SE. Column. It's just a row of values. Nothing special here. Okay, next one, this one. Size, it's an operator to measure sizes of arrays. Here I have like a sausage, horizontal array. I don't like to count something by hand. I use a size. Size, it's a measuring tool. I need to specify 2 parameters. One, what to measure, and second one is dimension. Number 1 is vertical. Number 1 is number of rows. Number 2, number of columns. If I would use a 3-dimensional array, number 3 will be number of layers. First, rows. Second, column. Third, layers. What's this? I will draw a chart. So here are omega t or double P divided by period values for each of the elements. It's just to draw a nice chart. It has no direct connection with Fourier role. It's just a variable for sum. Here, number of harmonics. How many components I would like to obtain. I will show it in future. In reality, there is one limitation for discrete time Fourier transform. For any, actually, it's a limitation for any digital processing of the signal. It's called Nyquist frequency because idea was put forward by Nyquist. And Nyquist idea, if we would like to stand on the ground, do something precise, we need to maintain sampling rate or distance between measurement point in such a way what higher of signal frequency will get at last or will be measured at last twice per period. So frequency of measurements, this discretization frequency, should be 2 times higher, at last 2 times higher than the maximum frequency of the signal. Or you will get a hell. I'll show it. I will show it in reality. In other words, distance of sampling, the sampling period, should be at least 2 times shorter than the period of the maximum frequency component of signal. Or hell will open. Here I'm taking 10 harmonics. Let's just see, remember 10. So I will try to decompose this into 1 DC component plus 10 AC component. For each, look at this. It's my sum. What I'm showing in blue is this part. Sum is 0 for each I from 1 to n capital. 1 n capital. Sum is sum plus signal value multiplied by cosine yi minus 1. Because I have an offset at a 0 point, angle is 0, but the first in array, first element has a number 1. That's why I need, since I'm calculating here from 1 to number of elements, I need to shift by 1. Multiplied by k, multiplied by 2, multiplied by language specific. Percentage sign in front of p means it's a constant. This point is language specific. It's a built-in constant of p. I don't like to write 3.1416 blah blah blah.
Isn't there the k missing here? The k in the formula on the form?
Yeah. Because this is for 1. Yeah, it's mine. It should be. I wrote a formula from the first one. Haha. Rare humanist. These 2, because I have 2 divided by n in front. That's why I'm putting these 2 rows. Yeah, and this part is this part, excluding this one, this is for DC component. C0 is a DC component. Next moment, I need to check. Did I write it correctly? How can I check my Fourier transform? Let's say I wrote a program. This program calculated something. I got set of cosine and sine scales of factors. Yeah? How can I check it? If I perform an inverse Fourier transform. If I do C0 divided by plus sum k say from 1 to n harmonic of cosine omega t plus st sine of omega t. What should I get if I do this? Original table. Result should match original table at the measurement points. Yeah? So, here is synthesis based on calculated C and S. If I did everything correctly, what I will get? Match between table and line. With the help of figure, create new plotting figure and plot two lines. One, this ST. Synthesis result. Draw it with the plus mark. And other one should be my table. Also, I have calculated, where are you? Here, average value of my signal. It's a DC, it's same as DC component. So I'm putting in, this means display, write it out. Also, this part, when you see RMS, what it means? Root mean square or effective value. Effective value or PC equivalent of my signal in theory RMS is square root 1 against period is from 0 to period s squared time. I will substitute it with square root of 2 divided y2 1 divided by n sum by I from 1 to n se squared. That's how I will calculate an effective value. Again, I don't like to do it by hand. Machine will do it for me. Sum 0. Take numbers from 1 to n capital to number of elements. Collect the squares and take a square root, but don't forget to divide by n because rectangle area is high by this. Here is my nice little program. Let's see, do it. What can it do? Oh, here is my chart. Green points are table, blue line synthesis. What would you say? Quite precise, isn't it? Where is some point? Can I get some mistake? Yeah, here it is. Fine. In my view, that's nice. And what about values? Here on console, I got results. Average, approximately 0, and it's 0, because it don't have DC component. And effective value, 66 volts. I can, sorry, sine and cosine factors. Here are components of my signal. Here they are. Also, I would like to show one thing. And this thing is effect of the Nyquist frequency. Let's say I would like not 10 but 20 harmonics. Yes, run. Impossible. See the result. It's because I'm trying to get more harmonics, what it's possible. I need, if I would like to get as much harmonics, I need a higher sampling rate. Here we see illustration of Nyquist frequency. What's the highest? Here, look at the difference. This line 20 and second line is 12. See the difference? It's an effect of Nyquist, of not obeying Nyquist limitation. Higher harmonic should have at least twice frequency, at least half of the sampling frequency, or nothing happened. Here it is. What can I what can I do? I can ask maybe some questions. I will put an example. Where I can put an example? I need to put what example somewhere. Maybe in a learning system. What's this? Wait 1 second. No, it's not. 1 second. I will put an example. No. I need to put an additional resource. One. What's the name? This one will be fine, I think. And where it is now? question. Here it is, but how can I move it? I hate this system. I simply, why I can move? No, I need to do this. Come on. Maybe this will be fine. Wait, it's not. No. Simple. This thing makes me you. Yeah. So this example will be. This is not. It's something different. Okay, you will get it in your learning system in front of lectures, so you can analyze it at home. Syllab is free, I guarantee. Just go to Syllab. And you can get, I use this one, but it's my problem. You can use new one. Free version. It's volunteered, now it's funded by the Dassault systems. Funded by the Dassault system, but it's a free alternative to quite expensive MATLAB. But it lacks the simulink part. You may bit more of programming. Okay. What else? What else? Maybe some questions? Too much of everything, yeah? But what's the conclusion for today? I will not start the next one. Conclusion for today. Fourier row works nicely, but if your function, if your signal has an interruption point, it will make a mistake. It will let's say, it will divert, or say it will not follow your signal precisely because Fourier row designed to converge averagely. In average, it calculates the basic of this Fourier theory is to rely on average error. On a sharp change, it has, let's say, backlash. It will oscillate around with the maximum deviation 18%. It's one. And second, every time you need to decompose something periodic in Fourier row, you can easily use discrete time Fourier transform. I can also say they are huge. If you ask your favorite Google or whatever, now everyone asks ChatGPT, what is discrete time Fourier transform? You will get an answer FFT, fast Fourier transform. Actually, it's a large block of algorithms optimized to important things you need to remember. First, native FFT requires number of measurement point, number of dots, being a power of 2. If not, it's or produce an absolutely useless result, check it, or it fails to roll DFT. CLAP library, if it cannot use optimized this flopping on symmetry, it will fail to DFT. Also, many standard FFT procedures do not normalize output. Don't forget to divide by n. And point number 3, you will get all this optimized power only if you calculate all harmonics. In our business, you know this, you heard about basics of electrotechnics, yeah? This foundation of electrotechnics theory. How do we calculate an AC circuit? We have some complexes, yeah? Some complex voltage, some complex current. What's the connection between complex from electrotechnics theory and real voltage? What hits me if I touch live wires? Where is this connection? Very simple. First, C1 minus J is 1 will give you this vector. So the vectorial or symbolic representation of AC current of voltage is the first harmonic of Fourier law. Just one tiny moment. C1 minus S1 minus, because Fourier law is written for cosine, not for sine as electrotechnics. But when I need to convert real current, real voltage to something unfamiliar from electrotechnics theory, here is a relay. It's waiting for the current to disconnect faulted line. If needed, I have these two boxes on top are amplifiers. I can upload fault recording and they will react. How can digital system get its current and voltage? By performing a discrete time Fourier transform. We have input signals, voltages, currents. They are processed by analog to digital converter. I have a flow of measurement dots. Sliding DFT procedure produces a flow of so-called orthogonal components, C and S for the signal in time. I need a discrete time Fourier transform, but only for first. I don't need higher frequencies. If I use an FFT, I will waste a processor time because I don't need a higher harmonics. I only need a base frequency. So DFT, not FFT. But actual FFT is an optimized DFT. It's everything simple. So we here on the screen we see what? Basic application of DFT to convert set of measurements into ideal components, and backward this part converts ideal components into real nice chart to compare them. Also RMS calculation. Simple. Simple. Okay, we have 3 viewers online. So, what so? Maybe some questions? No? No questions? Pushing this. Maybe our online viewers would like a question, ask a question. Who would like to ask a question? Nothing here. Okay, maybe someone will do something. What I need to do? Attendance chart. Come on, machine. I don't need this. I need what I need. I need attendance chart. Today. This. No, not this one. Not this one. Yeah, this one. Okay, here. Who wants to see his name on attendance chart? Like 22.